All right. So welcome again to chapter 6. Last time we started the first part of chapter 6, and today we're gonna have the middle third, and then the last piece will be for the following lecture. So what again? It's a big chapter. I just want to go through quickly the first third of the chapter, and then we're going to concentrate on the second third. So chapter 6 is all about needs analysis. So we need to establish using any payment management system. We need to establish what are the maintenance, rehabilitation, and reconstruction policies that really represent a significant part of any PMS. If I go to the field and I identify the problem, but I don't know how am I going to fix it, we are failing here, and there is no need for a PMS. The major output of a PMS is actually to recommend a maintenance, rehabilitation, or a reconstruction um, plan for the site that you just visited. So how we do it? Again, we do it through different types of policies. We can use only the network level, or it can be used at both network level or as well as project level. And then we've talked about how can we establish a MR&R at the network level. So it can be as simple as a decision tree, and if you have certain distress, you can do again and do nothing. If you did not see that distress or the extent and severity is very low, or you can go through a maintenance, rehabilitation, or even a reconstruction. Again, depending on how severe the problem, the problem really is. For example, here again, the one used at both levels give direct recommendations on specific treatment to be applied. For example, again, fill the cracks or an overlay. So if we have certain amount of cracks, depending again on the severity and the extent. If the severity and extent are very minimal, we tend to fill the cracks and be content with it. But if now the width of the crack is significantly higher than like 0.25 inches or so, then this is going to trigger the need now of we need actually an overlay. It's not just filling the crack is not going to do it. So the way we handle MR&R decisions, again, it can be using a matrix, it can be as a decision type or a life, and also we need to look into the life cycle cost method. So matrix or a decision type, it can be a decision tree, but then eventually we need to know again how much this each one of these options that we're recommending is going to cost us for the remaining life of that paper. Again, I'm not going to go through the nitty-gritty details here because that's been already covered, but this is here an example of asphalt concrete pavement distress types, MR and R alternatives. So here, again, let's say I have an alligator cracking or a fatigue cracking. Again, things can go from do nothing or to crack seal to partial depth real patch, all the way to other other techniques such as again skin patch or full depth patch. So any PMS, we need to come up with again such similar tables, or like Caltrans, for example, they specify first or they try to classify rather the cracks as classes. So class A would be longitudinal cracks within the wheel path, and then class B, that's an alligator cracking within the wheel path, and then class C, that's a special or unusual alligator crack. And thin AC overlay is thinner than zero point 0.1 feet. So zero point 0.1 feet, that's one tenth of a feet. That's how they define a thin overlay. And basically that's the solution for all of these three types of cracks that they may find. This is again another type of decision making tool, which is a decision tree. So if we have here a block cracking, or class A or class B or class C. So the A, B, and C, those are the ones that I just defined, but I can also have a block cracking. The next question would be, what's the percentage of the length of that crack overall compared to the overall section that I'm studying with cracks. So if it's again 0%, that's a very thin over. If it's 0% and If everything is very minimal, like the area patched is also less than 10%, then you can simply just do the fill the crack or very thin overlay. If you have again, that's for class B. For class A, which is a longitudinal crack in the wheel path, you typically go all the way directly to the filling the crack. If you have class C, which is an unusual location for an alligator cracking, again, it needs to be more a field investigation. Why? Because I know alligator cracking, I know how to treat it. If it's class B, that's alligator cracking. If it's class A, I know it's a longitudinal crack and I know how to fill the cracks. But if it's a special or unusual alligator cracking, before we do anything, we need to have further field evaluation to decide what kind of problem is this before I just go ahead and fix it. Same thing again applies to many other um, decision trees, if you will. This is here an interesting one, very important and very comprehensive type of tree. So the first question here that you're asking yourself, which in the middle, does this deterioration or does this distress that you see in the field, is it a structural deterioration or a functional deterioration? And we defined this early on in chapter 4, I believe. If it's a yes, it's a structural deterioration. Now you're going to ask yourself, is it low, moderate, or high? When it comes to fatigue, is this again, do we see fatigue? If it's low, then let's say you move on. The next question, do we have rutting? If it's a low rutting as well, then really the issue here is very minimal and you just do mill and fill with 40 millimeters. If it's a structural failure with high fatigue and let's say a high rutting, then that's a total reconstruction. You have a failed system. A high rutting, high fatigue, you can't really do much about. We have also again limitations for decision trees. Now this is really very important and it's a hot topic nowadays. The life cycle cost analysis, LCCA. Life cycle cost analysis is actually a big topic and people are looking into it and now more than before because we have multiple new technologies that we can use to fix roadways. And the question is, which one of these methods that you might be recommending is the most efficient and the most cost efficient method? So we've got to go through some sort of cost analysis in order for us to compare two or three alternatives. And it's not just the upfront cost. This is a life cycle cost analysis. We're really here looking into how much you're gonna put or how much money that you're gonna put in this structure in the next 5 or 10 or 15 years. So we've gone through some preliminary definitions here of some of the. This is again we're back to economics, if you believe it or not. So discount rate, which is actually the interest rate minus the inflation rate, and then we need to know what's the analysis period. When I put an overlay, for example, how long would this gonna last me? What's the unit cost of the treatment, and what's the estimated life of the treatment? Those are all four different important numbers. And again, the time value of the money. It's we all know again if you had $100 back in 1999, that's actually it's gonna be equivalent to about almost double if it's just 7% interest rate. In 2009, in 10 years, um, that would be 197 worth of uh, worth of money in 190 in 2009. Here more definitions of what's the discount rate. What I really wanna, again, we've covered this. Yes, here. Performance versus analysis period. Very important. What's the definition or what's the difference rather between analysis period and performance period? Analysis period, actually, this is the period where it begins when I start with a new construction and I end it with another cycle of a new construction. For example, I build a new road here in Tyler and it's built in 2021. And once that is being built, now I'm designing it for, let's say, 20 years. So 20, 41. This is the analysis period. There is a lot is gonna have a lot of activities. I know it's gonna happen between 2021 and 2041, but I'm not planning to do a major reconstruction until 2041, and that's what we call this is the total analysis period. Within the analysis period, I may have multiple applications of different rehabilitation techniques to keep me going until the end of the analysis period, if that makes sense. So, for example, as a new construction, I'm gonna have a brand new road. It's gonna last for me, let's say, um, till 2031 for 10 years. I'm building a new location, a new roadway in 2021. It's gonna take me 10 years before I reach, let's say, a PCI of 50 out of 100. Once I hit that date, I know I'm gonna do now an overlay to try to bring the condition back to almost to the original condition. Maybe again, not exactly at the original, but somewhere there. And now this overlay is gonna last maybe for 5 years. So that is 2036. So there's a performance period one, which is it lasted for 10 years as a brand new structure. And then now here we have performance period two for an overlay that's lasting for 5 years. And then I'm also gonna have another performance period three for another overlay from 2036 till 2041. And at this point now, again, based on my estimation and based on the budget forecasting, I'm gonna stop right here at 2020 2041, and I will have a major reconstruction. So I hope now you know the difference. Analysis period is way longer than performance period in most of the cases, where it starts with a brand new construction and it ends with a brand new construction. Within that analysis period, I'm going to have multiple rehabilitation activities or multiple maintenance activities that's going to continue to keep up with the health of the road. But for again, every one of these treatments is going to pump up the or is going to have a certain life, certain performance period, maybe for a year if it's a crack seal, or 2 3 years if it's a fog seal, or it can be for 10 years if it's a thick overlay. So that's again, so the analysis period somewhere between 20 and 30 years. That's typically what it is. For rigid pavements, it's actually 30 to 40 years. And again, as I'm mentioning here, in order to establish that the performance over the entire analysis, performance models are available. And in fact, most of the graduate students in this class, they are working now currently on term papers to predict what will be the performance of such of hot mix asphalt structures. What's the performance of what's endurance limit or what's the fatigue life of certain hot mix asphalt structures? What's the modulus of certain structures? What's the roughness of hot mix asphalt structure? All of these will help us to predict what will be the life expectancy, if you will, of those different rehabilitation techniques. So this is here the really in a nutshell. This is a good slide where it shows that the life cycle cost analysis, it's all about how much money are we gonna be contributing over the life of that treatment. So all of us can recognize this. In fact, even outside this class, people always look into how much is gonna cost me the upfront cost. This is the first cost. It's a brand new structure or it's a brand new location. I'm gonna have a lot of money being put as an investment from the very beginning as the first cost. And that's why the length of that arrow is actually the highest compared to the other costs. Really, the y-axis here, or how long or short this arrow is depending on how much money, the amount of money that, or the amount of investment that you're putting. So as a first cost, this is the big chunk of the cost. But then several years down the road, which is this is time, I know I'm gonna have some maintenance activities, preferably uniform maintenance to keep the health of the pavement at a high level. That is what I call routine maintenance cost. And then maybe 10, 15 years from the first cost, I'm going to have a major rehabilitation, such as a 4-inch overlay, compared to the routine maintenance, which can include, again, crack seal, fog seal, seal coating. All of these are routine maintenance, but the rehabilitation, again, we're talking at somewhere between 2 to 4 inches worth of an overlay. Then time passed, and they're going to have another routine maintenance and maybe another rehabilitation until you find the time where now there is certain fiscal year where you have enough budget to do a major reconstruction. But when you do that, sometimes by the time you are adding this last rehabilitation, it was supposed to last for 5 years, but strategically, you only waited until 4 years because at the fourth year you have the money, you have what it takes to do a major reconstruction. So what happens is this pavement was supposed to go for 5 years, but you are now ripping it off and starting it again at fourth year. So it had another year of life, if you will, and that's what we call it has some salvage value. What's the worth of the pavement structure at the end of the analysis period? Some of you know again that we try in the past 10, 15 years to be sustainable when it comes to pavement engineering, and how can we um, reuse some of those old materials. So that's what happens with the salvage value. I tend to crush that aggregates or that hot mix asphalt surface, crush it and use maybe you use it and mix it with a new hot mix asphalt mixture by somewhere between 10 and 15% or by weight, and reuse it again. If that pavement was fully exhausted at the fifth year, then maybe this is very oxidated. There is no need to use it, otherwise it might actually reduce the performance of the new structure when if I incorporate such material. But if it has some value, if it has some life in it, it's not fully oxidated, then it has a value. And that's why now the cost is in the opposite direction. All of these costs actually they are in the positive because you're gonna put money, but now the salvage value, now it has a value that you can make use of at the end. And your goal as a payment engineer is actually to sum up all these costs and compare them to if there's any salvage value, and come up with that what's the life cycle cost for this method versus another method versus a third method, and now you'll be able to pick what is the most efficient, cost efficient method that you're highly recommending. This is here what I was talking about. Imagine again the analysis period is for 35 years. The condition is 100, it goes down to 30. You have another um, you have another rehabilitation, goes back to 100, so on and so forth. But now you decided to end the analysis period right here, and that's why you have some salvage value over there. All right. So how do we do the life cycle cost analysis? Like calculation wise, we use two methods. The first one is the present worth method, and the second method is equivalent uniform annual cost. So the first one is the PW, the present worth, and the second method is the EUAC, and that's the equivalent uniform annual cost. So what do I mean by these two methods? The first one, the present method, as you could imagine, basically in this method we're trying to convert uh, any present as well as future expenses to the same basis of today's dollar. So if I know I'm gonna pay $100,000 in 5 years, I need to bring that back to how much does that equivalent to today's dollar. So the present worth of a future expenditure is actually equivalent to the amount of money that would need to invest now at a given compound interest rate, of course, for the original investment plus the interest in order to equalize it to what would be the expected cost at the time when it's required. That's basically the whole um, concept behind the present worth. So Let's say I'm gonna spend $1,000 in 3 years. I need to bring it back to today's cost, and I'm gonna spend another $1,000 in 10 years. How much that is equivalent to today's cost, and then sum them up, and then compare the different techniques and pick again the most efficient one. This is here I like to put it, and I'm and and visual way. So let's say again, these are all the costs that I'm expecting in the future, including again the first cost, the small routine cost, some bigger costs, maintenance costs, or even here major rehabilitation, as well as the salvage value. What I'm doing now using the present worth method is actually I'm bringing all of these as one number, as if I were to pay it today. How much would that cost? And then, of course, again, we need to, as I told you, you need to have a comparison to require similar analysis periods, of course. While the other method, which is the EUAC, which is the equivalent uniform annual cost, is actually it converts all present and future expenditure to a uniform annual cost. It actually again reduces all the costs to a common basis of a uniform annual cost comparison. Let me show you here a picture. What does that mean? Same thing, same example here. I have the first cost, I have uniform routine cost, not that much. I have some major, maybe major cost, and even a rehabilitation cost, including the salvage. Now what I do is I'm gonna come up now with a uniform cost. If how much would it cost me per year equivalent to the to this to these costs at different times. So really here the costs here actually represent the amount that would have to be invested in each year of the analysis period to match the total present worth of the project. So really here, what you need to do here, for the EUAC, you need to do first the present worth. You bring all the costs to the present worth, and then you divide them by how many years. So what are the inputs? How, if I know that there are two methods to do the calculations, but the process itself, it needs some inputs to have an effective life cycle cost assessment. These inputs including actually the agency cost. What's the initial cost for every single um, method or every single alternative that I have? And then what's the cost of any routine maintenance or rehabilitation that I'm anticipating? I need to define also what's the analysis period. I need to define what's the performance period for every application that I'm intending to have. I need to know what's the discount rate. I also need to know what's the cost of the salvage value. I need to know, which is very hard to get the last two, what are the user costs as well as the non-user costs. And we're gonna explain each one of these. So first, the agency cost. So we need to have a good understanding of what's gonna be the initial construction cost. What's the overhead cost? What's the design cost? Because it's not just a material. Again, every company has their own overhead, and also before we go to the field, we have to design it. We have to know and estimate what's the material quantities, what's the layer thickness of each one of those alternatives, and then what's the coverage rate, and then I need to know what's the unit price for each one of those, what's the length of the project, what's the construction procedure, etc. And then besides that, I also need to know what are the future maintenance and rehabilitation activities that I'm anticipating to do. Where do these costs actually come from? That's again a big question. An answer, one of the easy answers, again, if you go to Texas website, it actually tells you what was the history of all the bids that came out um, in the past maybe 5 to 10 years. So that's one of the sources that any DOT will keep record, is actually so we can understand and we anticipate what's the cost in the future projects. let's have an example here. So if initial cost, so if I have a 2-inch layer may actually not cost as one-inch layer because the labor involved in each operation is the same. Keep that in mind, please, because that will make a huge difference. It's not just the thickness of the structure, it's also the labor cost. So keep that in mind. Routine maintenance cost, I need to know that as well. Only maintenance activities that they are very directed, that directly again affect the performance of the pavement should be considered, such as pavement surfacing. That's common sense, I hope. Salvage value, that's also important. There is lots of different alternatives that will not end up at the same level of severity, or I mean, of serviceability. So it's also important to know if I add an 4-inch overlay, what would be the salvage value after 5 years versus what would be the salvage value of a 2-inch overlay. So really here you must give a salvage value for each alternative that is relative to where it's going to end up at the end of that analysis period. How can we get the salvage value? There is again similar or simple formulas here. It can be represented actually as a percentage of the initial cost. So the salvage value is equal to 1 minus LA over LE times C. LA, this is the actual life used, versus LE, which is the expected performance life, times the cost of that. So, for example, if I have actual life that was used was 4 years, while the expected performance life was 5 years, then what you need to do at the salvage value, you're going to say 1 minus 4 over 5. So that's going to be actually 1 over 5 times the C, the cost. What was the cost of that overlay? Remember again when I said again, I'm going to have the third one was let's say a 2-inch overlay. I know the cost of it, and now if I only have 1 year left, that means the salvage value for this material is 1/5 of the initial cost of this overlay. That's basically how we simply calculate the salvage value. How about the user cost? Very important, but it's very hard to incorporate. This is actually indirect cost. User, as it says, user cost. It's us as drivers, as users of the roadway. It's very indirect and it's non-agency cost. It's actually soft costs. They are very related, for example, to the roughness of the roadway or the serviceability history of that pavement. So it's very important that we need to include it because, again, the right quality that it has certain costs. It's gonna affect the again the right quality as well as the cost of maintaining our vehicles if we're driving on a rough surface versus a smooth surface. So this user cost again, as trying to summarize it here for you again, a strategy which provide an overall high level of roughness over a large time period, it will actually result in a higher user cost than another strategy which will carry again a traffic on a relatively smooth surface for most of the time. That's what I'm talking. So it will make a difference. What's the roughness, what's the serviceability between alternative one versus alternative two? A chip seal, for example, maintains a PSI or a PCI, but at a lower level. An overlay will actually upgrade the PCI to a higher level. So we may, you may start, let's say after 5 years, now you have two options. You have a chip seal or an overlay. An overlay is going to have a higher cost, but it's going to pump up the PCI or the PSI to a much higher level, and therefore the user cost will also be much smaller. So although you are putting a first cost or a rehabilitation cost, if you go back here, remember there was an R rehabilitation. So for an overlay, it's going to be way more than a chip seal. A chip seal might be very small, but if you add up the user cost actually for an overlay is very minimal. That's the user cost. versus for a chip seal, it's gonna be high user cost. So you need, that's why again you need to keep it in the calculation. Where again, how can we estimate, or how can we put all the user costs as one big category? It actually it's a big umbrella here that include traffic delay cost. Again, if you're stuck in the truck, if you're stuck in your truck, going back from work to your home for half an hour or an hour, that's money being lost. Again, you're, let's say you're working as an engineer, you're getting paid $70 or $50 an hour, and you're stuck now for an hour every day in the traffic because of um, doing an overlay. So again, you're gonna be wasting, maybe for the next 2 months there will be a lane closures, and therefore you will be delayed, and you're gonna be spending again an hour extra every day total between back and forth. That's $50, let's say, a day times 2 months. That's money, and times how many drivers are being affected by option one versus option two. That's the user cost. Travel time cost, you may not be again super delayed, but it might be, you might, instead of being delayed, you're gonna go through now another route that's gonna take you 20 minutes extra than usual. Let's say you used to go to work, it takes you 30 minutes, and now it's gonna take you 50 minutes. So that extra 20 minutes, that has a cost. Vehicle operation cost as well, whether they are again tires, fuel maintenance. If I put a chip seal, the vehicle, your vehicle is gonna be happy, trust me, and you're not gonna have that much of vehicle operation cost compared to if we put um, I mean let me take that back. A 2 inch overlay or a 4 inch overlay, the vehicle is not gonna cost you that much as an operational cost compared to if I just put a chip seal or just maybe even seal the crack. So the sealing the crack, it may have less first cost, it may have other advantages when it comes to other costs, but when it comes to user cost, it's not. It's actually the other way around. I hate to say this, but also even user costs that can include crash costs. Again, different alternatives or different maintenance rehabilitation techniques. It may contribute in a way or another to increase or decreasing the crash severity, and therefore the crash cost, and of course included in that the damage to the freight. So there are lots of models available on how to calculate the user cost. We're not gonna get into it, but I highly recommend, if you at your leisure, again, check out the three different types of models that they are available to estimate what's the user cost. I think that's what I was talking about. Again, as the pavement become rougher, again the operating speeds of the vehicle are generally reduced. So again, if it's a rough structure, your speed is going to be lower, and therefore you're going to spend more time on the pavement, and therefore the travel time is going to increase, the discomfort is going to increase, as well as other user costs will also increase. More frequent maintenance activities, again, it's going to end up creating longer traffic delays due to lane closure. So, and instead of saying 4 inch overlay, it's too costly, you're going to end up now having to close the traffic every year or every two to do crack seal or a fog seal. That's user cost. A lot of money being wasted just by picking a cheap option. Some agencies do not include user costs in the life cycle cost analysis. I'm seeing in the past 5 years, less and less agencies are doing that. They are really now looking into user cost as a major contributor into the life cycle cost assessment method. So, but back in the days, yes, which is a deficiency with the agencies, that they are not including user costs, because it's gonna save you a lot of headache from the public, from the community. You're not gonna get that many phone calls if you're doing a good rehabilitation technique, 2 inch or 4 inch overlay, and instead of every year you're going in the field having lane closures to do a crack seal or a fog seal. This is here a study that was done by Texas Transportation Institute, which is at Texas A&M. It shows that the annual hours for people stuck in traffic at Corpus Christi in an hour in a year, people get stuck in traffic for about 7 hours. In El Paso, it's about 11 hours. In Memphis, it's about 13 hours per person. So 13 hours times millions of people times how much that hours could have been spent in more efficient way during work or being with family. Uh, that's again, that's money being wasted as a user cost just by picking one alternative rehabilitation alternative compared to the other. How about now the non-user cost? This is even more complicated and it's more interesting. The non-user cost is also important, such as what kind of non-user cost is actually the loss of business due to the construction. If I'm having a major rehabilitation technique that's gonna require to close the roadway, local street, it's gonna affect it's gonna affect that local businesses. Those local businesses, not many people will go there. If that's assuming that they are allowed to go through one lane instead of two lanes and at that location. But assuming sometimes even they have to close the whole road, and people now will start to take other alternative roadways, and now all of a sudden there is not much demand at this location and at this and therefore all the businesses at that street they're going to be affected. So we're going to end up having lots of businesses due to the tours or closing a simple off ramp. So that's again, in a nutshell, again, those are the user costs as well as the non-user costs. The methods for again economic analysis. Let's here give you more details about how can we have an example and compare the two. So the two economic analysis, as I say, the present worth method and the equivalent uniform annual cost. Let's assume, or most of the time, we select a discount rate at 4%, and again the alternative which provide the least present worth or the equivalent uniform annual should be selected. Again, you as a payment engineer, you are going to end up picking one of the two methods and you stick with it, and now you're going to apply the same method you on in calculating what's the life cycle cost analysis for alternative 1, 2, and 3, and then you're going to pick which one is more efficient. And that's actually what I'm expecting you to do in your in the term paper and the term project as well. When you go to the field to know what kind of distresses, now you're gonna recommend for me 2 or 3 different rehabilitation techniques, and which one you're gonna end up being your number one technique based on the life cycle cost assessment. So this is here the present worth equation. So present worth for any technique is equal to F, which is the future sum of money at the end of n years, over 1 plus I to the power n. I, this is the discount rate, again, typically 4%, and the n, this is the number of years. Time, again, in future, when C again is up, when C is applied, when the cost is applied. While the other method, EUAC, now, what we need to do is that the recurring costs such as annual maintenance are already expressed as annual cost and doesn't need to be discounted. So the EUAC, as you could tell, we need first to go through the PW, the present worth. You need to do the whole thing and then multiply the present worth times I times 1 plus I to the power n over 1 plus I to the power n minus 1, which is basically here, again, the present worth, and then multiplying it by this ratio here, that's going to give you how much is going to cost us per year, knowing the fact that you know the analysis period, which is n, and you know what's the discount rate. If it's not given to you, again, it's safe to assume it's about 4%. A simple example here, we're going to have an analysis period. Let's say our analysis period is 20 years, and we have two options, whether to have overlays, like two consecutive overlays with time, or let's have an overlay and then we have a chip, then we have chip seals. So this is the first option here. First option is to have an overlay one that's gonna last for 10 years, and then once at the end of that 10-year, I'm gonna have another overlay that's gonna get me to the rehabilitation, to the analysis period of 20 years. So this is the first rehabilitation option. The second rehabilitation option is as follows. I'm gonna have an overlay. The first overlay is gonna last for 10 years, but then I'm not gonna do an overlay again. I'm gonna do actually three different chip seals. The first one is gonna last for 4 years, and then the second one is gonna last for another 4 years, and then the third one is gonna go for two years. But here, at this stage here, where actually there's no salvage value. Here, again, it didn't go down to the failure point, which is 2.5 out of 5 in this scale. It actually got truncated at this point right here. And the question here is, which one is more efficient? So we have to go through the life cycle cost assessment. Again, here, this is just um, going through the numbers. Again, we're not gonna go through again the exact numbers, because that depends on how much it costs, the unit cost for the chip seal and the overlay. But here I did the calculation using a set of numbers, and I just want to show you here the comparison between the two options. So option one, this is here the time in years versus the dollar amount times 1,000. So first option, I'm having a chip seal, I'm having an overlay, and that's why here is gonna cost me, this is here, let's say, 37.5 thousand dollars. And then I'm gonna have another jump, which is corresponding to the second overlay. And then I'm gonna have this jump. By the way, here, this is the annual maintenance, so that's why it's going this way. And this why, again, the same thing here, but this is the major rehabilitation maintenance, having the second overlay. And basically, this is the life cycle cost. We're gonna sum up all the costs here. The second method, or the second option, is again the cost of the first overlay, and then the cost of the first chip seal, the second chip seal, and the third chip seal. But including here, we have a salvage value. This is just a schematic here. I'm not discussing real numbers here, but you can do it. Well, how can we do it using real numbers? First, again, as I said, we to apply these numbers here, the PW, for example, F. This is the future sum of money at the end of n years. That's why, again, we need to go through all the numbers to get that future cost right here. Once you have this number, it's easy. You're gonna go back to the equation. You're gonna have this F, and you know how many years your number of years, which is 20 years in this case, and the I, this is the discount rate. So this is how you get the PW using this schematic here. So really what you need to do is you're just gonna put, this is the initial cost of the first overlay, and then there is a little jump. So this is here the cost of the first overlay, and then there is a little jump, the annual maintenance, and from here till here, this is the second overlay, and from here till here, this is the extra maintenance that's gonna happen, and this is now the total F value, the future cost, the total future cost. Once you have that, you're gonna go back to this equation. This is the future cost money, and then, so that's, let's say you have that number over 1 plus I, the discount rate, which is 4% in decimals here, to the power n. What's the n in this case? It's gonna be 20 years. And that's how you get the present worth for method 1. Same thing for method 2. For method 2, again, I know the cost of the first layer of the first overlay, and then I'm gonna have a little jump with the maintenance, and then I have another jump. So all these you need to know, and then this is salvage value on your which is again this is on in your favor, and this is the future cost right here. And then you're going to be applying the same equation. If you want to do the other method, which is the EUAC, that's even easier. Once you get the PW value from the previous step, you're going to multiply it by I. Again, you know the discount rate, and you know the N, which is 20, and you'll be able to compare the two different methods. So with that, again, we finish this what's middle third of this chapter. Next time, we will be talking more towards the performance models. How can we come up with predictive models to predict the future performance of the payment? Thank you.